ID the Future, a podcast about evolution and intelligent design.
Welcome to ID the Future. We've often been taught that homology is one of the best evidences for evolution. But what does the data really show? Hello, I'm Eric Anderson, and today I'm joined by Dr. Stuart Burgess. Burgess is Professor of Engineering Design at Bristol University in the UK. He is currently editor of 2 bioengineering journals and a lead designer for the British Olympic cycling team for the Paris Olympics. He was lead designer for the European Space Agency working on the Metatop satellites. He has had 2 research fellowships at Cambridge University and published over 200 papers on the science of design in engineering and nature. Welcome, Stuart.
Thank you.
Well, Stuart, we are today here at the Conference on Engineering and Living Systems. It's great to be across the table from you instead of calling from overseas.
Yeah, it's very good to be here.
Yeah, we're glad you could travel and be here in Texas with us and join us for this wonderful conference. So one of the icons of evolution, if you will, that we often hear about is the pentadactyl limb. And that has been put forward for decades as one of the great evidences of evolution. And in terms of a homology, one of the great examples of how the human hand or the human foot is similar to the whale fin, and therefore this proves evolution. In fact, I had just pulled up a few minutes ago, I just searched pentadactyl limb in Google, and the very first hit said, this is from biologyonline.com, it says a limb with 5 digits, such as a human hand or foot, which are found in many amphibia, reptiles, birds, and animals, which can allow us to deduce that all species derived from one common ancestor. Well, first of all, it's not a deduction, but we'll set that aside. It would be an inference. But why did you get interested in the topic of the pentadactyl limb, and in particular the whale fin?
Well, I'd seen in the media that it attracts a lot of attention. And I mean, just to give one example, in 2021, there was quite a famous photo where a scientist in Denmark, he got a beak whale, and he actually dissected the flipper, and he brought out this quite dramatic structure, which was like a hand, in fact, similar to the size of a human hand. And there were headlines around the world saying, oh, this proves that whales have this leftover trait from their kind of land ancestry. But I could immediately see that there were very good design explanations to this. So I felt very motivated to explain to people that this icon of evolution, it was actually a very weak argument.
Yeah, so there's a number of things we could talk about in terms of the pentadactyl limb argument. You can look at the sizes and the shapes and those types of things. But what I wanted to focus on today, because it really goes to your area of expertise, is the structural engineering side. And so let's talk a little bit about what it takes to build something like this. But first, let's analyze the evolutionary argument. Why is this an argument that they put forward, and why do you think it's a weak argument?
Well, they're saying that this pentadactyl limb, you have this common structure with fingers, often 5 digits, and the wrist and the elbow joint and the shoulder joint. So they're saying surely this means that one creature is an ancestor of another. But what they're not doing is looking to see if this is actually the best design for all of these different applications. They're not considering that at all. And not only that, but they're, for example, not looking at the whale flipper and saying, well, it would actually be better if it was this design and not that design. They're not doing those things. They're not analyzing the requirements. So it's quite a superficial argument that the evolutionist is putting forward.
Well, surely no designer worth his salt would make both the human hand a pentadactyl structure and the whale fin a pentadactyl structure, right? I mean, that's kind of the argument that's laid out. That's the way it's popularized, is surely no designer would do that because there's no good reason for that. And so it must be a result of some evolutionary history.
Well, if you're a designer, you're always looking for the optimal design for that particular application. And when I look at the whale flipper, I cannot think of a better design than a 5-digit hand-like structure. Because if you look at the requirements, a pectoral fin, the flipper, it has to very precisely move into different shapes. So what mechanism are you going to produce those finely tuned shapes? Because whales have to maneuver very precisely. If a killer whale is trying to chase a penguin or a seal, penguins and seals are very agile. They can change direction suddenly. So the killer whale needs to move its flippers extremely precisely, and you need some kind of hand structure to change the shape of that flipper.
So what do you mean change the shape of the flipper? I mean, a lot of us might think, if we're not familiar with this, that you just have a flipper, it sticks out there. You can move the flipper, sure, but what do you mean by change the shape of the flipper?
Well, the flipper is a hydrofoil. It's basically a control surface.
Mm-hmm.
So on an aircraft, you have control surfaces. On other systems, you have control surfaces. Even when you're swimming, you have to move your arms in very specific directions to change direction. And the whale relies on its flipper to do that. And you need to change the shape lengthways, but also even in a cross section,
Mm-hmm.
in order to get these fine, precise movements to change the trajectory of the whale.
Okay, so just for our listeners, so we can understand a little bit, if I've got my hand and I hold it up with all the fingers together, you're saying that I could maybe cup the hand a little bit or bend some of the fingers in and have a different hydrodynamic shape if I do that?
Yeah, cupping is a good example, but also twisting.
Mm,
Sometimes you need to twist the whole of the pectoral fin. You've got to remember that the whale doesn't have many control surfaces. It powers through its tail.
mm-hmm.
Apart from that, it cannot change direction. And a whale is so heavy, it would find it so hard to change its movement. So these flippers are a very essential part of the whale, and they have to move very precisely.
How large can these get in some whales, if we're talking about a flipper?
For the humpback whale, it can go up to 15 feet in
Okay.
length, and some of the forces on it can be over 1 ton. So we're talking of very big structures and very strong structures. And again, there's an important point here that in order to withstand a load of over 1 ton, you need very strong structures inside that flipper. And a bone with tendons and muscles is exactly the kind of solution that you need. Whereas a little fish might have tiny ribs
Mm-hmm.
in their fins, that's not any good as a design solution for a whale. It needs these super strong structures.
Right. Okay. So we've got some massive forces being applied to these fins in these larger whales. And wouldn't it be better, somebody might ask, to just have one big, strong bone that goes out all the way to the end so that you've got this huge, strong structure that can support all this weight?
Well, that certainly would be very strong, but the problem is you couldn't then get a nice curvature in that flipper. If you look at some beautiful pictures of humpback whales, you notice how their flippers have a very smooth curvature when
Mm,
they bend. You can only do that if you have multiple bones, and that's needed for hydrodynamic efficiency. And not only this, but research papers have been carried out dissecting various whale flippers to look at their musculature, their muscles and tendons, and to the surprise of some researchers, they found that whale flippers are full of flexor muscles and extender muscles, the kind of muscles we have in our fingers. They're obviously being fully functionally used in these
okay.
flippers. So the evidence is showing that flippers do need all of these finger muscles and movements.
Okay. And this is a really important point, kind of on the side of what we're talking about. But back to the icon, one of the arguments is, well, we've got some stuff that's vestigial, is the term used, or it's left over. Maybe it's not really performing an important function because, gee, you just got the fin out there. Why do you need five? We'll call them fingers. They're not fingers because they're not human fingers doing what we do with our
Yes.
fingers, but we'll call them fingers for purposes of the discussion here. You've got five fingers out there in this flipper. They must just be leftover detritus from the evolutionary history.
Yeah, that's just not true because those 5 fingers are absolutely fully functional, as shown by
Hmm.
the research, finding that they're fully functional because you need to change the shape of that flipper and you need multiple digits to do that. And even applying some engineering analysis, you could argue that 5 digits is actually an optimal number because, on the one hand, 5 digits gives you enough to make a smooth curvature in the flipper, but not only that, it's a low enough number to give you strength in the bones. Because if you have too many little bones, the bones are not very strong because the stiffness of a bone is proportional to the cube of its depth. So that means it's better to have a small number of big diameter bones than a large number of small diameter bones. And so it turns out that 5 is actually an optimal number from both a stiffness and a curvature point of view.
Okay, let's dive into that just a little bit because I know you stated it, but walk us through again just so we can understand. So, if we have one large, massive structure, it's going to be very strong, but it's going to lack flexibility. Is that what you're saying? And
Yeah.
ability to make some of these fine movements. If we have a whole bunch, let's say 10 or 20 fingers instead of five, you've got lots of ability to make movements. But you gave us some math just a second ago. Talk us through that. Why would that not have the strength that you need for this tonnage that the whale is supporting through this?
Yeah, maybe to give you an example from an aircraft wing, which is itself a control kind of
Mm-hmm.
surface, it's recommended that you have these deep section ribs to stiffen up the wing because you get a lot of stiffness through having a very deep section. So if you've just got a certain amount of bone material, rather than using that to have lots of little bones, you're
Mm-hmm.
better off having at least a few bones with a big diameter, which gives you that depth, which gives you that big stiffness, as we often see in engineering in all kinds of structures. And as I say, it so happens that five gives you this trade off number. Engineering is full of trade offs.
Right.
You're rarely just maximizing or minimizing something. You're getting the best compromise between two extremes.
Mm-hmm.
And whichever way you look at it, five is a good compromise from a stiffness point of view and a shape point of view.
Okay, so if I'm trying to build a foundation of a building and I want to sink a pier, I'm probably going to use one big, thick pier for that particular corner. If I'm trying to build, I don't know, something that's much more loose, that's going to flutter around like a wing or something like that, it might be less. But in this case where we've got, but even the wings of Pentadactyl, actually, that would be another example of some movement there. But in this case, you're saying that there's some optimality. So the story is that we had this leftover, and that's based on this idea of homology. And we see that there's similarities, but you're arguing that the similarities are due to a purposeful design, right?
Yeah, in engineering, it's well known that a common designer gives common design. So you could look at the design of the space shuttle and see bolted interfaces, nuts and
Mm-hmm.
bolts, and bearings and other parts. And you'll see those very similar parts in a train, in a motor car, in a
Right.
bicycle. It's very common to see common design. And going back to the pentadactyl limb, you could compare a robot with a digging machine and a space robot arm
Mm-hmm.
and find that they all have a shoulder, an elbow, and a wrist.
Right.
So this is a kind of a universal design. Engineers are taught to, if you have an arm system, then you always have a shoulder, an elbow, a wrist. So for an engineer, it's very natural to see this universal design appearing in different parts of biology.
Right. The other thing that I thought was interesting that you had mentioned earlier was this idea of the structure of the arm, and you see this both in the human arm and the whale limb, although there are some important differences we could talk about in a minute. And that is that you begin with one large, strong bone, and then that, as you go toward the extremity, that turns into two smaller bones and then three smaller bones. And talk us through that a little bit.
Yeah. So this is another design feature of the pentadactyl limb, which is really an optimal feature for two reasons. With most limbs, you want to twist them. In the case of the human arm, if you have a screwdriver, you turn the whole arm. In the case of a whale flipper, they also want to twist their
Mm-hmm.
flipper. When you're twisting, you want to gradually do the twist through multiple joints, through gradually increasing the number of bones. So it's optimal for twisting. But also, if you're transmitting compression loads, it's always better to do that going through one bone, then two, then three, then four. You're reducing your shear stresses and reducing the chances of buckling. So, from a structural point of view, that's exactly what you would expect to see. So, again, that will be a reason for this common layout, the humerus bone, the ulnar radius bone, the wrist, and the five digits.
Okay. So it sounds like it's a pretty optimal design choice in terms of the pentadactyl limb for what the whale needs, as well as for what we need. Is there any other aspects of optimality that you wanted to bring out, or?
I think that covers it. But just to make the point that if it was true that the whale had this leftover relic of design. It would be easy to propose a better design,
Hmm.
but I've not heard anyone propose what would be a better design for the whale flipper.
Okay, so the evolutionists have commonly said, hey, no engineer worth their salt would do this. It doesn't make sense in the whale. There's a better design, but you haven't heard any.
No, I'm still waiting.
Yeah, that seems to be par for the course. I wanted to ask you one more thing about the whales. The other aspect of the whale physiology that's often put forward as a vestigial organ, maybe not so much homologous, but well, I guess partly homologous, but certainly as a vestigial organ that's useless, is the pelvic bone structure.
Yeah.
Tell us about that a little bit.
Yeah, there have been some claims that you can see relics of leg bones coming out of the
Oh,
side
okay,
of
yeah, yeah.
whales. But in 2014, in the Harvard Gazette, researchers admitted that they now realize they're not vestigial at all. These bones inside the whales, near where the pelvis would be, they actually help support organs. In fact, the reproductive organs of whales. Everything is large in a whale. So they realized they're fully functional. They're not vestigial at all. So that came out in 2014. But sadly, since then, there are a lot of biology books that haven't corrected that, and they're
Right.
still wrongly stating these as vestigial parts.
Yeah. Okay. So relatively recent data, but it certainly shows that when you don't know what something is doing, it's a bad idea
Yes,
to assume it's not doing anything.
exactly. Mhm.
So another concept that you talked about is this idea that you proposed of extreme homology. What do you mean by that?
So what I mean by that is some rather extreme cases where things are so similar, you could only really explain it by planning. So one of my favorite examples are marsupial rats and placental rats. So in Australia, you can find a marsupial rat, and it looks from the outside remarkably similar to placental rats that you
Hmm.
get in America or Europe. And the analogy I would give would be two, say, BMW motor cars. One is an EV car, the other is an IC engine car, but on the outside they look almost identical. Now that requires planning. An engineer planned the fact that
Right.
you had identical body shells, but inside was completely different.
We've got a car that's selling well. People like the look of it. They like the feel of it. We want to keep that the same, but we're going to completely swap out the engine, probably make changes in the drivetrain, probably 100 other things or 1,000 other things that you have to do to make that
Exactly.
happen. But it looks like the same car basically until you look at the tag on the back and realize, oh, it's an EV.
Because it had very good aesthetics. It was
Hmm.
selling for good
Yeah,
aesthetics.
right.
The intelligent designer creates this beautiful placental rat
Hmm.
and then thinks, well, let's have the identical body shell and make it a marsupial one
Right.
for a bit of fun, for good aesthetics. And I think that's very hard to explain by evolution because if things change so much on the inside, how could the outside be just
Hmm.
so very similar? So,
Right.
so that's what I would call extreme homology.
Okay, interesting. Is there anything in the molecular realm that's similar to that? You're talking about organisms at this level, but
Yeah, well, I've done some literature surveys, and it was so fascinating to find that these similar structures are found in molecular biology. In proteins, for example, you can find very similar protein structures in very different situations in different creatures. And even within one creature, the same protein structure acts as part of for example, in a bird, one protein that does something in the lens of the bird is also doing something in some digestive cycle.
right.
And I think some of the researchers have been astonished to find some of these similarities. But as I was saying before, this is what you'd expect from a common designer reusing solutions in different applications.
Hmm. Yeah, I think one of the researchers used the word moonlighting. We think this
Yes,
protein that we thought was doing X, we now found out it's doing Y, and so they said it's moonlighting as Y. But
it's got a day job and then
yeah,
a night
right,
job.
exactly. But it's a structure that is valuable and can be reused for a different application
Yeah.
in the same organism even. Okay, interesting. Well, anything else that you want to share with us with respect to this idea of homology? Do you think the idea of homology is something that points toward design generally or points toward evolution generally? I mean, do you have a feel for where that argument is going as we get more data coming in?
I think it's a really fruitful area of research,
Okay.
and especially as engineers are now collaborating more with biologists, I think this is an ideal area to come out because in the past, biologists not knowing engineering maybe didn't know how to tackle this whole area of homology, but now engineers are so often getting involved. I think it's a really good area for researching.
Yeah, well, that's a very interesting approach because I think even for folks who've been skeptical of evolution or in the design movement, we often hear homology and we think, okay, we don't agree with the storyline or the narrative that's been attached to that, and that homology is something that we kind of need to defend against or attack. And what you're saying is, yeah, that's fair enough in terms of the evolutionary story, but there's actually good reasons for similar structures in different types of situations, different types of systems. And so we can kind of take that on the offensive, if you will, and say, look, there's reasons why design would make sense in this case, and maybe we need to revisit some of these homologies that have been classic, icons of evolution, to use Jonathan Wells' term, and see if there are good design reasons for these. And maybe it even becomes then an icon of design rather than an icon of evolution.
No, that's exactly right. We need to articulate it, and we need to get design experts in particular fields to articulate why that is actually the best design for that application.
Excellent. Well, Stuart, thank you so much for being with us today. We're really glad you were able to fly all the way over here and participate in the conference. We really appreciated your contributions and the talks that you shared. So thanks for being with us.
Thanks. It's great to be here.
Thank you for joining us for this episode of ID the Future. To hear more about the important work carried out by scientists that shows evidence for design in nature and helps us better understand our own origins, join us again here at ID the Future or on our sister YouTube channel, Discovery Science. For ID the Future, I'm Merrick Anderson. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.